So first of all, I will try to wrap up our discussion regarding the linear mixed model. And we will also talk about some of its extensions. And then I will spend some time talking about different ways to do model selection. Suppose that we have multiple models with varying complexity to describe, to fit to the same data. Then which model will we choose as our model to do the inference of our parameter of interest? So first of all, let me try to write our linear mixed model again, LMM. So the matrix form we write, if you recall from our previous lectures, is y equals x beta plus z delta plus epsilon. Okay, so in this model, only this part is fixed. And the random parts, including delta, epsilon, and y. So when we specify the distribution, we specify, I'll just write it without the explanation again because we talked about this. Delta, it depending on how you formulate it, but delta basically is a multidimensional vector representing random effects. So we assume that it follows a multivariate normal distribution with zero mean vector and a covariance matrix we call G. And epsilon is an n by 1, right? Because we have n observations. So we can also say it follows a normal distribution, zero mean, and covariance matrix R. But in many cases, we can simplify it as just normal distribution, zero mean, with a common sigma square times identity matrix. So if you simplify in this way, then the sigma square is your error term variance. And it's important to assume that delta, random effects, and epsilon are independent. So a reminder is that the reason we specify delta to be random is because we don't want to estimate so many parameters. Instead, we just want to say there are some effects that are different in how to say, they play a role. There are effects that are non-zero, but we don't care about their specific values. So therefore, we just want to assume that they jointly follow a distribution. So in our previous example, we consider epsilon delta to be, say, school-specific intercepts or school-specific slopes. And across different schools, these delta follow common distribution. So then the question is, we just need to estimate this G, the covariance matrix that controls how the school effects are different and related, correlated. Okay, so then we talk about parameter estimation. So if we use this formulation, which is very common, just a sigma square, then the parameters we need to estimate are just beta, G, and sigma square. These three things, we need to estimate them. So basically, once we are here, then how do we estimate G? Has two ways. So recall that last time we said, oh, when we estimate beta, the estimator by maximum likelihood estimation would involve G and sigma square. And typically we do plug in. So we will find estimators of G and sigma square, plug them into the beta estimate, and that's it. Or if you think, oh, in the linear model, if in the linear model, your beta estimate is just, basically we have that X transpose W X inverse, X transpose W Y. The W matrix is what? It's what you have as the aggregate error term. So remember, we have a formulation to call this epsilon star. So if we have the epsilon star following its own covariance matrix, that covariance matrix can just be the W to enter in the MLE formula. So you can just treat this as a linear model, linear regression, but the error term is not the IID one. That's another way to say it. But at the end of our last lecture, something we said specifically is regarding how to estimate the variance components, G. So in many studies, we are interested in G. So the parameter of interest. So if interested in G, the question here is, do covariates in Z have effect? So this can be an interesting question to answer because in our school education example, you may want to ask, do different schools within the district, within the same school district, actually have different effects on the students' performance, right? Do schools have different effects? If you want to ask this question, then the hypothesis testing you are going to do is essentially this G equals 0. But here this 0 is a 0 matrix, okay? So if you want to ask this question, then it is important to have a good estimator of G. So the question is how to best estimate G hat. Okay. And remember that last time we gave you 2 ways to do it. And this is also something you will see in the literature, which is ML estimate G hat. Okay, so in this case, the G hat will be estimated together with beta hat. Okay, so let's just ignore sigma square for now. You can also think of them as together, sigma square with G hat, G. But for now, let's just talk about G only. So this will be argmax of the likelihood of beta and G. So you will need to write down the likelihood to do the MLE and to find G hat. An alternative is that you would, we call this REML, restricted maximum likelihood estimate G hat. So in this case, this G hat is not a maximizer of the likelihood together with beta hat. Instead, it is argmax of the so-called marginal likelihood of G. And the marginal likelihood is by integrating out possible values of beta. So beta is no longer an estimate, but you only, beta is no longer a parameter, but you only have G left. So where LMG is the integral of the likelihood beta G d beta. So you're doing this. You integrate out beta in the likelihood function. So last time we said, oh, which one is better depending on what your goal is. So let me first recall that there is a difference between MLE and unbiased estimator. So let's first remember that if you recall this problem, so if you have just a linear model, okay, in this case, so beta is P by 1, epsilon is a normal distribution, 0 mean, sigma squared I. So the parameters here are just beta and sigma squared. So remember, if you just do the MLE, so essentially you want to find beta hat and sigma squared hat jointly as the maximizer of the likelihood. Okay, if you do this, then a well-known result is that sigma squared hat is 1 over n, summation I from 1 to n, yi minus xi transpose beta hat square, average residual square. But we know that this is actually biased. Even though it's asymptotically unbiased, but it is biased on the finite sample case, because you know that the unbiased estimator should be sigma squared hat 1 over n minus p. This should be the unbiased estimator. Then what's the difference between this unbiased estimator and the biased MLE? The difference is in the degrees of freedom. So one way to interpret this is the unbiased estimator actually accounted for the degrees of freedom we use to estimate beta. Because beta is p-dimensional, so we spent p degrees of freedom to estimate beta. So we're only left with n minus p degrees of freedom to estimate sigma squared. But in the ML, maximum likelihood estimator over here, essentially, this formula is derived by assuming beta to be fixed. So that's why given a beta, this is the ML, E for sigma squared. But here you didn't spend any degrees of freedom to estimate beta because we treat beta as fixed. So we're doing 1 over m. Even though we are actually plugging the beta hat here because beta is unknown. So you see here, what is missing in the MLE is that you didn't account for the degrees of freedom spent to estimate beta. Same thing here. Same thing of estimating G. So when we use ML to estimate that, essentially we are assuming basically for given beta, what is the maximum likelihood of G? And then we plug in that beta hat. While for the marginal likelihood approach, in this case, we remove beta from the function. So we don't need to spend any of our data to estimate beta. So we save the degrees of freedom for estimating G. So that's why in practice, if you want to say, which one would you choose? So the question is depending on whether G is your parameter of interest or beta. So let me just quickly say this. So which one to choose? Which estimator of G to use? Okay, to answer this question, ML or REML? Okay, so the answer depends on whether you are interested in beta or G. So if beta is the parameter of interest, use ML. So in this case, beta, for example, if you want to test beta is 0, or if you want to test whether a component of beta is 0, that means you can remove that covariate from your model. Like in our nested model selection problem, we have a model without the jth component, the smaller model, and we have a model with the jth component, a bigger model. You want to decide whether you want to go with bigger model. So these are all the questions related to beta. So in this case, you want to use the maximum likelihood estimator theory to get the asymptotic estimation, asymptotic distribution of beta hat. So in this case, you also want in this case, G is called a nuisance parameter because it's not our parameter of interest, but it's just something we need to account for. We use the ML for maximum likelihood estimator for G. But if G is the parameter of interest, use REML. So this is the case where you want to test whether the random effects has any zero or non-zero variance covariance matrix. So in some applications, this might be of your interest. So besides the school example, so something I can also say is that, for example, if your data is a location data and spatial data, this is very commonly used. So for example, if you want to ask this question, does the spatial location have any effect on the income? Okay, on person's income. So in such a case, you may have, for example, yi as, for example, ith person income, and we may have, say, xi as some ith person gender and age and education level. So the factors that we know will determine the income, education level. Okay, and besides this, we also want to account for this person's spatial location. So we can call this SI to call the ith person's spatial location. So for example, if we are just using the address of that person, then we can convert the spatial location to latitude and longitude, right? Longitude. So you can basically have the SI to record this person's two-dimensional location in the world map. So in this case, if you want to have and how to say model to do that, then you will think for these covariates, gender, age, education level, their values are fixed. You only have a finite number of possible values for each, but the spatial location can be, how can have many values depending on how high the resolution is you have for the location. If your resolution is high enough, maybe for one single location, you just have one person. So therefore, you cannot really afford to have a parameter estimate specific to each location, right? Because that will give me too many parameters. So in this case, a very natural way is to say, oh, I have delta SI as the effect of location SI. But as I said, for SI, maybe you only have one person at this location. So then if you have n persons, then you will have n such deltas. That will be too many. But one thing that can be reasonably assumed is that, oh, maybe these effects are correlated in the way that nearby locations may share more similar deltas. So therefore, what we could do is that what we can basically stack this location effect into a vector. Okay, assume this to be an n-dimensional Gaussian distribution with mean 0, and we can specify the covariance matrix to be something reflecting the proximity of the spatial locations. So a typical way to assume this to be a degree of, variance, tau square, multiplied by a kernel matrix. And the kernel matrix is an n by n matrix that depends on the S1 to Sn. So the kernel matrix can be a thing that will give you similarity among nearby locations and dissimilarity among distant locations. So for example, one common kernel is called the Gaussian kernel. So in the Gaussian kernel, what you have is, so basically K, Si, Sj, between locations Si, Sj, the Gaussian kernel will give you an exponential function of the negative SISJ distance. I'll just put it here, SISJ. So you need to have a distance metric that is reasonable between spatial locations. It could be like Euclidean or altitude distance. It could be other types of distance, but you need to have a distance here, and typically it's the altitude distance, and we put a square of the distance and then divide it by some 2 times, I'll use a different notation, maybe, I use sigma square already, maybe omega square. So this is just to define the bandwidth of the Gaussian kernel. So in other words, the larger the omega square, you will consider larger neighborhoods as in proximity, while if omega square is small, you only consider very nearby neighborhoods to be in proximity. So basically, the Gaussian kernel gives your presumed similarity or dependence among spatial locations of their effects. So in other words, the Gaussian kernel is your specified pattern for the spatial locations, and you multiply them by the sigma square as the degree of variance. Because this kernel itself doesn't carry it with it a degree, right? The variance could be small or less given the same pattern. So you have this thing. So if you have the model formulated as this, then if you want to answer the question, does spatial location have any effect on person's income, then your null hypothesis is simply reduced to testing whether tau square is 0. Because if that's the case, then this delta S1 would be equal to delta Sn. There's no difference among them. And that means, oh, the spatial location doesn't have any effect. Does this make sense to you? Yeah, so that's why in the variance component test, a lot of the cases we need to specify a kernel for the covariance matrix structure. And then when we do the test for the variance component, we're not really testing a whole n by n matrix to be 0 or q by q matrix, depending on dimension of delta matrix to be 0, but just a scalar being 0. So that's that. Coming back here, I'm saying the G matrix may be specified as a scalar times a pattern you pre-specify. Okay, so I would say in R, you will have this package to implement the linear mix model. So it's called MLE4 package for implementing a linear mix model. Okay, how about other types of model? So just as that we have linear model going to generalized linear model, how about linear mix model? How do we generalize it? Okay, so if we turn the page and say, okay, GLMM, generalized linear mixed effect model. Where do we generalize? So if we just, let me see. If we have the generalized linear model as a comparison, okay, remember that we have the 2-layer structure, random and systematic. In the random structure, we have yi independently following exponential family mu I, okay, with some potential nuisance parameter sigma square. Under the systematic structure, we have the link function that links mu I to xi transpose beta. That is the GLM. So now, if we want to introduce random effects, my question for you is, which layer should we introduce the random effect? Is it the first layer on yi distribution, or is it the second layer in the systematic structure about g of mu I? How g of mu I depends on covariance. Where should we introduce the random structure? Any ideas or any thoughts from our students? I have a chat box message. Random first part. How do you do it? Where would you put that sigma, or not sigma, delta regarding the random effect? Where do you put it? Remember what I wrote, if you remember, what I wrote in our last lecture about 3 ways to represent the linear mixed model. The second way is the hierarchical model, right? So we first sample delta from the random effect distribution, and then condition on delta, we have a linear model. We have a linear model's random structure, that is yi is distributed as a normal distribution, whose mean is xi transpose beta plus zi transpose delta, right, with variance sigma squared. So similarly, here, it depends on where we will put the random effects on. And I will say we always consider the effects to be on our mean, right? It's on our mu I, it's not on anything else. So in that case, we would just change the model to be, for the random one, it will stay as yi follows exponential family, mean mu I, variance sigma squared. We have the same thing. But for the systematic structure, we will have G of mu I, not just depending on fixed effect covariance, but also depending on random effect covariate. We have this, right? So in other words, the random effect will affect the mu I. It's just that we don't want to have delta fixed. Instead, we need the delta to vary. So in other words, this systematic structure now has a random component because this is random, which will make mu I random. That is the difference. So now the systematic structure will become random. And you will need another layer to specify the distribution of delta. Okay, so you need another layer to say that delta follows normal distribution, zero mean, covariance matrix G. And this is multidimensional. So basically what I'm writing here is this is one-dimensional scalar. This is one-dimensional, but this is multidimensional. So together, this gives us the generalized linear mixed model. But to find estimates for, again, beta, G, and the nuisance parameter sigma squared, depending on whether your exponential family has this nuisance parameter or not. Because if exponential family, for example, the example is Bernoulli or Poisson, they are just one parameter distribution, then you only have mu I, right? You don't have the other parameter. So in that case, you just need to estimate mu I and G. And you can still do the likelihood-based inference. You use the likelihood to maximize it to find beta and G, beta hat and G hat, or you can do the REML by integrating a beta, then you find G hat. So the idea is the same. It's just that the optimization becomes more challenging as you go from linear mixed model to generalized linear mixed model. Does that make sense to you? And this will be the case when your yi is not Gaussian. It's unlike a normal distribution, normal variable. So the values are not continuous, but maybe binary or counts. Okay, so any questions before we wrap up this part? So I think this generalized linear mixed model is the one that just embraces all the components we talked about in this class. including how do we specify a model in a hierarchical way. So essentially, if your model involves random parameters, you need to specify a different layer for that parameters distribution. And when we say regression, the systematic structure is the key. That is, we are trying to link the expectation of the outcome as some function of the covariates or predictors. Then, so in the linear and generalized linear model setting, even if we need to have some transformation to make mu I and xi linked, we only apply the transformation, the link function, which is a monotone function on mu I, but we still keep the covariates part to be linear. And this linear means that we didn't transform the covariates themselves, and we are adding up their effects. So there's an additivity. So the effect of different covariates predictors add up, and also we are not transforming the covariates as themselves. Yeah, so this makes the interpretation very easy because we know that for the beta j, the jth component of beta, we can specifically say, oh, it is the effect of the covariate j, predictor j, among all my predictors. And beta j means that if that predictor's value increased by one unit, how much increase I would get in the g of mu I as an increase. Okay, so that's all. And then for the last part of our class, I will talk about a very big topic. We will only give you a very high level idea about what it is, but I hope that this can be useful in your use of those methods. It's called model selection. So this is something we should actually perform before we do the inference, because it is a way for us to choose among possible values and pick the one that can help us explain our data well enough. Okay, so model selection is always choosing between, let me say, if you do likelihood-based inference, then it's about, how to say, maybe I'll just say in a high-level way, that is the goodness of fit versus model complexity. Okay, so how do we do it? So essentially, the idea is always in this trade-off of model complexity and goodness of fit. That is, if I have a highly complex model, I can perfectly fit my data. But if the model is too complex, I don't think the model can generalize well to a new data set that I don't observe. But I can say that this idea has been challenged by the current advances in AI, where we can assume, maybe largely assume that the training data we use to fit a model is the whole thing, right? It covers everything we see in the world. So in that case, maybe your new data cannot be something different from your training data, or it's already contained in your training data. So you wouldn't see this so-called generalization error. So let me just say it. For this question is regarding small training data that could be for small training data. And so you're worrying about this so-called overfitting issue. You don't want that. So this overfitting issue is reflected in the fact that the model complexity, if the model complexity goes up, right, then the overfitting goes up. So the goodness of fit is getting better, but the generalization error is getting worse. So you will perform worse on a new data set. And so that's why you are not necessarily preferring just a complex model. And goodness of fit, if you're not doing the test, right? Remember that we have the goodness of fit test by comparing a generalized linear model with a saturated model. In that case, the saturated model just has the perfect goodness of fit, right? Has the perfect fitness. So if you're comparing a GLM model to that model, we understand that in terms of the likelihood, then the one for generalized linear model is definitely smaller than the likelihood for saturated model. But we're just hoping that their difference is not big enough, so we can still say, yes, the GLM fits good enough, fit well enough. So that's the general idea. And so in reality, when we're doing the likelihood-based parameter estimation, then the goodness of fit is essentially reflected. How well does data fit to the model to fit the data is essentially using the likelihood. So, which give us higher value if fits better to the training data, to the data we have at hand. Or another way you can use if the method or the model you want to analyze doesn't have a well-defined likelihood function, or if the likelihood function is difficult to calculate, you can just use the prediction error. So in this case, it could be sum I from 1 to n yi minus yi hat square. So depending on how complex your model is, you will get a different y hat. Then, in the extreme scenario, your prediction error can just be 0, right? If every yi hat is just equal to yi, then you don't have any prediction error. So this is one aspect. And for the model complexity, this is often reflected by the number of model parameters. So in our linear model case, if you're interested in the fixed effects, it will be P, right? How many predictors you include in your linear model. Okay, so regarding model selection, if you are looking at the prediction error as the goodness of fit, the most commonly used procedure is called cross-validation. That is the thing many people use to evaluate machine learning models, like whether the model has enough predictors or too many predictors. So the most common is cross-validation. Some people write it as CB. So for cross-validation, the idea is the same. That is, you evaluate prediction error on leave out data. So basically, when you do your model fitting, is that you apply only a portion of your data to train the model. So you can learn the model parameters from those data. And then you apply the model to the data you leave out without using in the training to calculate the prediction error. And as you can do that in a cross way, right? So for example, if you have, so the commonly used 5-fold cross-validation, common 5-fold or 10-fold cross-validation is the most commonly used. The idea is that if it's 5-fold, every time I leave out 1 fold for evaluation, And some people also call this the testing data, right? They will have the, validation data. Validation data, you leave out one field for validation, and you use the other 4 fields to train a model. And you can do this in 5 different ways, because each time you leave out one field, so the other 4 fields will be used for training. This will give you 5 prediction errors. And then you take the average of the 5 prediction errors as your final cross-validation error to report. So this can allow you to evaluate the model prediction or generalization error, because you're not using the data for training. But I would say cross-validation, even though it's very simple and universal, it has some, how to say, subjective choices in its usage. For example, how many fields? And it is, I have to say that until recently, there has been some work on understanding the theory of cross-validation. For example, how do you find the trade-off between having too many fields or too few fields? I want to pause here a little bit to let you think, what is the advantage and disadvantage of having too many fields? Let's say on the extreme, you can do leave one out cross-validation. That is, every time you leave out one data point and use the n-1 other data points for training. What is good and bad about it? So the hint is to think about a comparison with the model you would train on all data points. Because in reality, in applications, the model is usually say trained on all the data available. And then hopefully the model is good enough, and then we can just apply the model to any future data points, right? So we want to use all data points to train the model for future use. But for cross-validation, we cannot use all data points. We have to leave out some data points. Then what is the advantage of leaving out many data points, but versus not leaving out too many in each field? Okay, so I will give you the answer, and you can decide whether it makes sense to you. So the rationale is, if each field is too small, the good thing is your training data will be close to your whole data set, right? Because if you have leave one out cross-validation, your training data is n-1 data points. It only differs from the real data, the data you want to use for building a model, by 1 data point each time. So essentially, the model you are evaluating is close to the actual model you want to get. So this is the good thing of leave one out cross-validation. But the bad thing is that your prediction error each time is only based on 1 data point. Okay, so the prediction error does not reflect the real scenario where you would apply your model to a new data set. That will most likely have more than 1 data point. And also because having 1 data point, that will make the prediction error itself to have a large variance each time. So even though you can still average across the n folds, but each one has a large variance. Okay, on the other hand, if you just have 2 folds, so in this case, the evaluation data is large. So the prediction error you obtain from the validation data with half of data points doesn't have a large variance. But on the other hand, the model you're evaluating is only based on half of all data points. And this could be quite different from the model you are going to use, which will be trained on all data points. So that's why I'm saying the first question for cross-validation is the number of folds. And the second disadvantage is that you are not going to use all your data points. And this may be a bad thing if your total sample size n is small. And this is the case for many medical data. You don't have such a large n. And you don't want to, maybe, for example, you may only have, say, 20, n equals 20 data points. And if you do the cross-validation, you will get an even smaller sample size, and that is not desirable. So I would say here are two questions or disadvantages. So you have to choose number of votes. And another thing is that you're not using the full data set. So basically you waste some data points. Okay. So that's cross-validation. And also cross-validation is a computer-based technique. You must have computers to be able to do cross-validation. You cannot do it by hand. So therefore, in the old days, again, before computer was widely used, there were some quite interesting techniques that allow you to do model selection without splitting your data. And the two most popular ones are AIC and BIC. So they don't need data splitting. They can just use the whole data set to fit the model once and then evaluate the fitted model. Okay. So just for your information, this A is a person's last name. The author of the AIC paper, his last name is Akaiki. Okay, this is where the A stands from, and B comes from Bayesian. Okay. So on a high level, let me explain what is the different use of AIC and BIC. So they are under different logics and for choosing the model. So, and this is quite theoretical. So it's a theoretical way of thinking about model selection. So AIC doesn't assume that, okay, among our candidate models, there is a true model. So it doesn't have this assumption. Instead, what it tries to do is to find the model, find the candidate model that gives the best prediction accuracy. So essentially, it tries to find a model that best approximates the data distribution. Because if we assume that the data comes from some underlying model, but we don't know its true model, we have a set of candidate models, and we know that all models are wrong. But we hope to find the candidate model that best approximates the data density, and this can be approximately set as maximizing the prediction accuracy. Even though AIC is still a likelihood-based approach, instead of calculating prediction errors directly. But its idea is try to find the model that maximizes the data, that best approximates the data. Okay, while BIC is more, how to say, ideal in the sense that you're trying to find the true model among candidate models. Okay, wow. So this may seem to be a little bit unrealistic, right? How can the model among our candidate models to be true? But this is what BIC is formulated under the idea. So essentially, BIC, when we say Bayesian, we are assuming that each candidate model has some probability to be the true model. So in other words, we will have a prior distribution on our candidate models. Yeah, so that's the starting point of BIC. But interesting thing I can tell you is that AIC and BIC, if you use them in practice, you would have different model choices in some cases. So in other words, let me first write down the AIC. Okay, so AIC is defined as -2 times the log likelihood of the theta hat. And theta hat is just the parameter theta's MLE estimate. So essentially, you are using the log maximum likelihood here, plus 2 times D. D is the number of predictors. Or maybe let me just use the notation we are familiar with, 2 times P, to be simpler. So P is number of parameters. So in this case, you can see that if a model has a large likelihood, then large log likelihood, then AIC will be small, right? The -2 times log likelihood will be small, negative. And P, model complexity, will be added to AIC. So in other words, you will prefer a smaller AIC because a smaller AIC indicates that, oh, the likelihood is large and there are not so many parameters. Okay, but you can see that if between two models, if one model has a larger likelihood, but the difference in their -2 log likelihoods cannot be compensated by the increase in the number of parameters. Like if the increase in 2p is bigger than the decrease in -2 log likelihood, then AIC will be increased instead of being decreased. So therefore, you wouldn't choose that larger model. So in other words, you can see this 2p as, how to say, as kind of like a penalty. It penalizes the model complexity. Okay, so on the other hand, BIC has a different formula. -2 log likelihood theta hat plus log n times p. So essentially, you can see that you are getting the same likelihood based on maximum likelihood estimation, but your penalty on the number of parameters is much larger, is log of n. So essentially, if you use BIC, you will more likely choose a smaller model than a bigger model compared to AIC. This is also consistent with AIC's preference for prediction accuracy or model's goodness of fit, because AIC prefers a bigger model to explain the data better. But BIC is more ambitious in saying finding the true model. So it just turned out that after its derivation using the Bayesian argument and also under it uses some normal distribution techniques. So basically, it's called Laplace method. To use, I'm not going into detail, but it's actually in our lecture notes, the last lecture notes, if you're interested in. So using that technique and using the Bayesian argument, they will actually get this log n out as the penalty. So essentially, we can say that each method or each criterion have its own argument. And which one would you use? And interestingly, very similar to people's choice between a frequentist approach or Bayesian approach in doing statistics on a particular data set. The choice of AIC and BIC, I would say there's no black and white argument to choose one versus the other. It's more about whether your preference is on a smaller model for maybe better interpretation versus a slightly bigger model for better prediction accuracy. I think it's more like that. But most importantly, I have to say that both require this thing. So they are techniques for low dimensional data because they both require n bigger than p. Otherwise, they won't work. Okay, so that's why for high dimensional models where p is bigger than m, it's a totally different realm. So we cannot use the classical techniques here. And let me see. Another way to compare between AIC and BIC is to think about from a model selection is to think about from a posterior perspective, which I think is quite interesting. So in other words, we can show that if you use the BIC's argument to interpret the model selection criteria for AIC, then essentially you would have this. So it's actually in the notes, last notes 18.4, comparison between AIC and BIC. Because of time limit, this time I will not go into the detailed derivation of that, but I'll just quickly say this. So essentially, if we have this BMJ, let me just see here, just introduce this notation a little bit. It's the candidate model J. Okay, so we can show that if we are following the AIJ way to select the model, then essentially we have the prior of MJ equivalent to this exponential function of 1/2 times the PJ. PJ is the dimension of model J times log n minus PJ. So what does it mean? So essentially that when we use AIC, we don't have this prior specified, but we're just saying that what if we use AIC to select the model but provide a Bayesian interpretation like BIC? What is the corresponding prior does AIC put on different candidate models? And from this, you can see that AIC would prefer a larger model in its prior interpretation. So just using the BIC way to interpret AIC. So this is like the BIC interpretation of AIC. So AIC would actually prefer a larger model because if the sample size is bigger. So basically, as n increases, AIC prefers a bigger model. And this is different from the naive, the default implementation of BIC, where it doesn't have any different priors. It put all MJ's priors as the same. So that's BIC. But if we want to use that to interpret AIC, this is something we get. So now the question is whether you think this is a reasonable argument or not. Because if you do, you think this argument of AIC makes sense, then AIC should be your choice. You want to have a bigger model if your data sample size is bigger. But in the BIC interpretation, since it believes in the true model, then the true model shouldn't change with sample size. So that's why it's not in favor of this argument. Yeah, so I think this becomes something subjective. Okay, and also in the notes, if you want to you are interested in knowing the detailed derivation of AIC, it is based on some KL divergence. So I think the idea here is interesting. So it's worth talking a little bit about so you can see the argument or the whole idea of deriving AIC. So I'll just quickly say this. So the idea behind AIC . is that when we have data y1 to yn, IID following some f, which is the density function, is the density function. I'm assuming just continuous random variables. Okay, and we have models, a candidate set of models, which we can write as M1 to MK, a total of K models with parameters theta 1 to theta K. Okay, so each model has its own parameter. So then if we use the model to express the density of yi, then we can say that under MJ, under model J, we would have yi follows, or yi's IID follows this density function P, which is just specified by theta J. So under the model, the density is specified by theta J, but the true model is just this abstract expression of F. So then the KL divergence, which is a quantity in information theory, quantifying the difference between two distributions. That is, how is one distribution deviated from a true distribution. So in this case, we actually can write it as expectation, which is under the true model, and it's y following f, right? That's the true model of this log ratio of densities. So we have f of y, the true density of y, and p of y given theta j. Okay, so this is the objective we want to minimize, because if it's small, it will indicate that our model density, which is p y given theta j, is not far away from the true model density. So one step to go down is to just express this as a difference. So we have expectation, and again, it's y following f distribution of log fy minus expectation y following f distribution, the density p y given theta j. Okay, so the objective of minimizing the KL divergence, so our goal is to choose J to minimize the KL divergence. And this is actually equivalent to maximize this thing to be subtracted, because this one, the first term, has nothing to do with the model, only the second term is related to the model. So it's actually equivalent to maximize this. Oh, sorry, I lost the log here. It should be log P Y, right? It's this one. And this is essentially, it will remind us of the likelihood, because under the expectation, it is the log likelihood. It is the log likelihood. But we actually have the expectation with respect to y. That means we are considering all possible y's, not just the y1 to yn we observe. Okay, so therefore, there are two things. So first of all, when we try to find this by maximize j from 1 to k among the k models, we want to maximize this. There are two questions. First one is that theta j is unknown. Okay, we need to estimate. We can estimate as theta j hat MLE. Second question is expectation is unknown. right? We don't know the true distribution F, then we cannot calculate this. And this can be estimated by Y1 to Yn using the data and use the Monte Carlo method to estimate this expectation. So essentially, you see that we would estimate this term as 1 over n summation I from 1 to n log p yi given sigma j hat. So we will use this term, which we can compute instead of this term. And this is what? This is actually 1 over n times the max log likelihood. Because the sum across the log PYI is our definition of log likelihood, right? It's just that. So if you're just using this to maximize it, you will always choose the most complicated model. Because as we said, the more complicated model, the bigger the likelihood. What is the problem here? The problem here is that you have a bias, and this bias is actually due to the fact of using the same data twice. So it is the same Y1 to Yn that you use to estimate theta j. It is the same Y1 to Yn you are trying to use to calculate the average as approximate estimate for the expectation. So you are using the data for twice, okay? So Y1 to Yn are used twice, and there is a bias. And this is very similar as using the training error to approximate or estimate the generalization error. The fact is that you already use the data to train the model, then of course the training error is small. It will be smaller than what you get from a new data set. So the same idea here. So then what AIC has been doing is trying to come up with an estimate for the bias. That's the whole thing. So AIC tried to come up with a way to estimate this bias using its very smart mathematical argument with some Taylor expansion techniques involved for estimating the bias. But essentially, and also it uses some central limit theorem-based result, large sample theory, which is something I will talk about next quarter, like a class I will teach next quarter, large sample theory. So using that result, finally, it came up with the error term, and the error term actually is only based on the number of parameters. So that's where it came out. So essentially, what we get here is that using this term, using this to approximate this, okay, this one to approximate this, and they found that the bias is just dj over n. So essentially, you are getting a larger term here, larger than the actual expectation by dj over n on the order of that because of the double dipping bias, because it uses the same data for twice. So I think AIC is just a very interesting way to derive this result. And you know, this is very important in the old days without computers. It means that as long as you can compute the likelihood function by hand, you just add this number of parameters into your model selection, and then you can avoid overfitting. So that's the idea of AIC. And BIC follows its own logic to do that. But I want to say that AIC has a corrected version. The corrected version is to correct for this term bias is not an accurate estimate if your n is too small. Because as I said, deriving the bias, a lot of asymptotic approximations were used for assuming n being large. But if n is small, then these arguments don't hold well. So for example, people will say when d over, oh sorry, I should say pj. I got confused notation myself. If n over pj is less than 40, that's some practical rule of thumb, which means your n is not big enough. Then there is something called AIC corrected version, or people call it corrected AIC. And that stands for AICC. So in this case, the AICC is actually 2 times L theta hat J for model J, or I would just say AICC for model J, is this negative to log likelihood plus 2 times PJ. This is AIC. And you add an additional term, 2 times PJ times PJ plus 1 and minus PJ minus 1. So you have this additional term. And the use here is that you are actually, when n is small, you're adding a larger penalty for model complexity. So compared to AIC, then this AICC will more likely choose a smaller model. And some people have empirically shown that if you use AICC, it's actually closer to BIC in model selection. Yeah, so that is just the classical result people play with, and you see the how to say the value of doing this is that you save your data from cross-validation. Otherwise, you have to split your data, and that will make your training sample size too small to get a good model. All right, so this is what I want to say for this class. And actually, this year we had some cancellations due to holidays, or I mean, no class due to holidays. So that's why for the last part, I had to be a little bit brief and only give you the high-level idea. But I will say maybe for users, it is more important to understand how do you choose a criterion for evaluating your model, right? So we skip the details for derivation, but I hope to still make the high-level ideas, how to say, reasonable to you. So if you have any questions, yeah, just let me know. You can stay in the class, in this Zoom to ask your questions, or you can come to the office hours to ask your questions. Hopefully, this class materials will be useful for you for your research, in particular for our PhD students. And for our master's and undergraduate students, I hope the materials will be useful for your future study. Yeah, so yeah, linear models, even though they are considered to be the classical simple models, but still there are a lot of things we can say, especially how do you come up with a reasonable model for your data? Bearing in mind that all models are wrong, but why do we still have some models to be useful, right? So why are they useful? That is the most important question we should think about when we develop a statistical model. Okay, so that's all I want to say for today. And as this one is on Zoom, so I will post the recordings. So if you want to watch again, or if any classmates missed the class, they can watch that. Okay, so thank you all, and I'll see you at your presentations.
Thank you.